that will help you if
Oh,
that's
okay.
showing up for you. Um, so one of the things on Canvas on our end is sometimes it shows up for things show up for us, and we need to go into some menu somewhere and click some option to make it show up for you. So I need to just go figure that out. That will help you. Okay. Yeah. So let me figure that out and yeah. So other than the homework this week, what else is going on? Anything else you want to discuss?
Yeah, I have a couple questions. The first one would be Canvas is being weird. It says I can't take the study quizzes because I'm not enrolled or whatever. I don't know why. I checked my balance on Access Plus. It's zero, so I should be okay there. I
Okay.
don't
Yeah.
I don't know what's up with that.
You may notice a recurring trend that Canvas's interface, like there's lots of things that can give you lots of fine control over everything, but it's a mess. So yeah, I don't. It could be something on your end. It could be something on my end. Let me check my end to verify that there's not some problem there. So which study quiz in particular are you having a challenge accessing, or is it all of them, or any?
Uh, the one I've been using to check is chemical equilibrium one, but let me try one of the heat and mass transfer ones just to be sure. Yeah, no, I can't take any of them. It
Okay.
says only registered enrolled users can take graded quizzes. So
Uh,
I emailed David Welshans about that. He hasn't gotten back to me yet,
you
so I
you
can
you
probably
you
email him
you
again.
are enrolled though, right? And registered.
Uh, I believe so, yeah, because it sent me an Access Plus bill, so I should be fine.
Yeah, that is odd. Yeah, so let me see. I can look to see if other people, no one else has asked me specifically about it. Um, but it seems like at least, oh, hold on. Is this a real student or a dummy student? It looks like one person has done this, I think. Let me see. Uh, okay, yeah. So people have access to access to it. It's not just you. It's not. This could be something that's on your end. So yeah, contact David. The other thing is IT services. You can reach out to them. So you can find their website in either in Canvas, or if you just type in I would say IT services. There's like a one email that you deal with all the IT, and they'll route it to the right person. Um,
Okay.
so yeah, this happens occasionally for students. I don't know why. And they usually can identify what is the holdup, or whether on their end they also need to just check some box, and then you get access. So yeah, sorry you're dealing with that. That's frustrating.
It's Canvas. It's whatever.
Have you used the Canvas before in your previous institution?
Yeah, Penn State was all Canvas.
Yeah, so you're used to this.
Yeah.
Yeah, you seem to be handling it like it's normal. So I think that when people get introduced to this, they're like, "What is this horrible system?" So yeah, anyways, so we will keep me updated with anything uh that you're any challenges you're running into, and I can always see if there's something on my end. In this case, it looks like other students can access it. Um,
Okay.
yeah, so anything else?
Well, I guess I can get into content questions.
Yeah.
So from the homework, question one, I had a few because I haven't done a lot of this before.
Mhm.
So how do you determine if an azeotrope exists? Is there like a specific way to do that? Because I went through all of the chemical equilibrium stuff, and I think I have a pretty okay handle on that.
Yeah. So azeotrope. So the question first is like, what is an azeotrope? So here, let me share my uh screen with you. You can see my screen?
Yes.
Great. The question, oops, what's going on with white? Azeotropes. So first thing is, what is the azeotrope? So if you look at a phase diagram for, so there's two types of phase diagrams that we'll commonly look at with, especially for vapor liquid equilibrium systems. So there's what we call a TXY and PXY diagrams. So in these, T will be temperature, P would be refer to pressure, Y generally will refer to the vapor composition, and X would be the liquid phase composition. So these notes will be accessible to you. If you can go ahead and write down, but just to let you know.
Okay.
Okay. Okay. So generally these will look something like this, and you probably saw these in the reading. So you have temperature versus X1 or Y1, where this goes between 0 and 1, right? Where 0 would be where X1, where when the x-axis reaches 1, that would be pure species 1, and when the x-axis equals 2, that'd be pure species 2 for two species system. The following so far.
Yep.
So suppose you have components 1 and 2. Okay, so you'll have two curves generally. So if you have an ideal solution, let's draw that out first. Let's look at 2. So let's map out a few points. So if you have pure species 2, this temperature here would be the boiling point of 2. The temperature here would be the boiling point of species 1. That makes sense? You have some temperature where it goes from vapor to liquid to vapor when you exceed that temperature. And you'll have two curves. One that goes something like that. And another one that will be like that, right? So this will generally, so for ideal solutions, you'll always get some kind of diagram with this type of shape. So this is what we call the bubble line. Because if you're going up in temperature from this somewhere in this bottom region, when you reach that line, that's when you create your first vapor bubble. It's a saturated liquid before then, and when you hit that line, it becomes a phase that's in equilibrium with vapor, right? And we call this here the dew line, because up at this higher temperature, everything is vapor. And when we go down, then you start getting condensation or dew, like dew on grass. So here will be a mix of vapor and liquid. Okay, so for ideal solutions, azeotropes don't exist. Azeotropes are conditions where the vapor composition of the mixture and the liquid composition are the same. So the classic example is ethanol. So if you buy, depending on the state that you're living or have lived in, you can buy Everclear, this type of alcohol, which is like ultra pure alcohol. So depending on the regulations in your state, you can buy up to 95% alcohol, which they call grain alcohol. And that's the maximum you can get by distillation. Because if you have a non-ideal solution, so suppose you have an azeotrope, your phase diagram will look like this. They'll meet somewhere in there. This is the azeotrope. Okay.
Yes.
So there's a number of ways that you can identify whether there's an azeotrope. So you can graph this out, for example, these diagrams. And that's something that's not too difficult to do, but maybe it's cumbersome. With the computer, if using Excel or MATLAB, it's definitely something that you could do. You can do this mathematically too. So the most straightforward way is to let me pull something up. Is to look at what's called the relative volatility. And I think your textbook covers this. I want to verify that. Let me try to find the page. In the Matsuka's textbook, let me find the place here. I also want to try using the same symbols and terminology that they use, since we're using this textbook for this class because you can access it for free, but I teach from a different textbook, so every textbook sort of talks about things in a slightly different way. This one is pretty similar to the one that I use, but I just want to make sure that I don't start using some symbols that you can't follow. Okay, let me open this up. Okay, so let's see. So there's a discussion of azeotropes in chapter 12. If you look at figure 12.7.
Okay.
In text. Okay, so here's mathematically, here's the way that you can term this. So at the azeotrope, X1, the liquid phase composition of 1 equals Y1, right? And the liquid phase composition of 2 equals Y2, the vapor phase composition. So the reason, and that's the reason why you can't distill above that, because distillation relies on the presence of a vapor phase that has more of one species than the other. So once you reach the azeotrope composition, the liquid and vapor phase are the same in composition, and you can't distill anymore because you'll just be distilling the same composition over. Does that make sense? So it's an important functional thing to understand about azeotropes. It's from the standpoint of chemical engineering, it's a challenge with regards to separation processes. If you want to make an ultra pure material, chemical, if you run into azeotrope, you need to do something different. Okay, so we can write, so these non-ideal solutions, so azeotropes are something that only occurred for non-ideal solutions, and they typically you'll use modified Raoult's law to describe this. Should have seen a video about that.
Yep.
So this is YIP. So Y1P equals X1 gamma 1 P1 set. And Y2P equals X2 gamma 2 P2 set. Okay.
Yes.
So one thing that we know, so we know what we're trying to identify is that I believe in those problems you're trying to find the at constant pressure, what is the temperature at which an azeotrope could exist, and maybe the other way around. If I recall, I asked you to do both. Okay, so a couple things. So suppose we know the pressure, but want to know if an azeotrope exists at any temperature. Okay. So the nice thing about the azeotrope, so we know the pressure already, right? We also know that X1 equals Y1, right?
Yes.
So at azeotrope, X1 equals Y1, X2 equals Y2. So these cancel out, right? Because they're equal to each other. You can just divide through.
Mm-hmm.
So we know the pressure, and we have an expression for activity coefficient, right? That's given to you, which is a function of temperature. And the saturation pressure is also a function of temperature, right? Through the Antoine expression. So we have, what we need to do is identify, is there a condition where a temperature at which this is true, right? So because this is going to be a complex formula, since the activity coefficient is sort of as a log in it, and the PSAT is a polynomial expression, the Antoine equation. So that means that you can use either, my recommendation would be you can use MATLAB if you're familiar with MATLAB. You can use Solver in Excel or GoalSeek. But it's relatively straightforward at that point. You know, basically so are you familiar with any of those tools?
Yeah, I've used both.
Okay, yeah. So usually that's, so for some students, depending on your background, they haven't had experience with those. But you know, since if you know, for any, I'm recording this, so if any of the other students haven't seen any of those type of tools to solve these types of problems, let me know, and I can help guide you through that, because it's not difficult, but if you've never seen it before, you probably need to could use a starting place. Right. Does that answer your question?
Yeah.
And so this is actually the more challenging of the two. If you know the temperature, you can plug the temperature into the PSAT equation. You can plug the temperature into the activity coefficient equation, and then you just need to solve for pressure. right? So the solving for pressure at a known temperature is more straightforward. So I went through the more challenging of the two things that I asked you to do. Okay.
Yep. Okay. And what is the Antoine equation? I've never seen that before.
Okay. So the Antoine expression. Let me. Okay, so Antoine expression in the textbook is in there's a note in chapter 7 in the section of vapor equilibrium. Here, let me write this out. So this is what we call give page numbers as it. In chapter 7 in the textbook, we can find a section or something. Section 4.2 about vapor liquid equilibrium. 7.2 in text. So the Antoine expression basically is a formula, is an expression to give PSAT. So log PSAT equals minus minus A over T plus C plus B, takes this form. And for any species, you can look these up in a table.
Got it.
So these are tables that you can find. So there's some will use slightly different terminology or symbols, or they might write it in a certain way. And it doesn't really matter which one you use, whether it's this one or a different one. They should give you about the same answer. And they're empirical equations that describe the vapor pressure as a function of temperature for a given species. So these are things that you can look up at in the NIST databases. For example, textbook should have a table of these as well.
Got it. Okay.
Okay.
Thank you.
Yep. Yeah. Good question. I'm sure some other students will have these. So thanks for asking.
Okay. And then bubble pressure.
Bubble pressure.
I haven't seen that before, but
Yeah,
I have
so
a feeling it's similar to earlier.
yeah, so here I drew a TXY diagram, right? So this point right here would be the bubble temperature, right? At that pressure. So if you were to draw a PXY diagram, that point would be the bubble pressure. So
Okay.
in the textbook, it should go through. No. Sorry, looking in the wrong search box. I was looking for books with the title word bubble in the title. Let's see. Yeah, so in chapter 11, here, let me. Chapter 11, it goes through those calculations just directly. Chapter 11.3, and it goes through it using Raoult's law in chapter 11, and the way to do this for non-ideal solutions is follow the same process, but you have activity coefficient in there, and it probably goes through that later in the textbook.
Okay.
Okay. Yeah, but the problems that I'm giving you are based mostly off of examples, or can be extensions of examples that you find in the textbook. So that's always a good starting point for these. Okay.
Yeah. Okay. Thank you.
Any other questions?
Yeah, I think question 2 is that Is that a semi-infinite solid boundary condition? I was just wondering.
Remind me of the question again.
It's asking you to here. I have it pulled up.
Yeah, sure.
Problem 2. Oh no, that's not problem 2. It's sorry, problem 3. A membrane of infinite depth.
Uh-huh.
I was just wondering if that meant semi-infinite solid.
Yeah, so when we were talking about, so that's pretty directly telling you the sort of assumption that you need to make there.
Yeah. Okay.
Mhm.
That's good. I just I have to go through and rewrite down, I guess, all of my assumptions because I have them all in my notes from previous semesters, but I have to like put them all in one place so I can see them again because there's a few that I forgot, like what they actually do to the OD. But
Yeah, so I think, since there seems to be an accessibility issue with the heat and mass transfer stuff.
oh yeah, I forgot about that.
Yeah, so I'm probably going to give you all an extension on the homework. I want to make sure that you're not. It probably shouldn't take you super long, but still, I want to make sure you're all the time. So just to give you a heads up, and I'll let everybody know on Teams. So yeah. All right. Anything else any other questions that you have for now?
Last one is I saw in the on the canvas that said something about a microscopic energy balance. I've never seen that before. Is that in the heat and mass transfer textbook, or would that be in
Yeah.
another one?
So heat and mass. So I guess the idea is microscopic energy balance versus macroscopic. That's something relevant to heat and mass transfer, and it'll be there.
Okay,
And that relates to, rather than taking like a bulk fluid, taking some differential component of it.
got it.
Okay.
Yeah. All right. I think that's most of it.
Okay.
If I have any more, I'll send them in Teams.
Yeah, definitely do that, and happy to help. Let me work on getting you access to half what you need for half of your homework, and let me know if you need anything else.
Yeah, thanks. I'll send an email to Penn or to the Iowa State IT after this.
Okay, sounds good.